The latest Gemma 4 model released by Google comes in three variants. We have the dense model, the MOA model, and the effective model. The dense model is obviously the most high performance model. It performs very well across all benchmarks, but it has a couple of drawbacks. First of all, it's not very memory efficient and it's not very compute efficient as well. The MOA model, basically the mixture of expert model, solves one of those problems, and that is the compute efficiency. It's more compute efficient when you're running inference, especially, but it's also not memory efficient because you have to load all of the parameters into memory. The effective model, on the other hand, solves two of these problems, both the memory issue and the compute efficiency. So basically in this video, I will be diving deep into the concept of effective models because they're sort of like very new in the large language model space, especially they were first introduced in the Gemma 3N, and this is the very first time that we're actually seeing them like take center stage in the Gemma 4 models. So basically the effective models take advantage of a concept known as per layer embedding, and we will be diving deep into the whole concept of per layer embedding. So in this video, I'll focus on one of the variants of the effective models because they come in two variants, and that's the E2B and the E4B. So I'll just be focused on the E2B model, and yeah, so let's get started. So in order to understand the whole concept of per layer embedding, let's dive deeper and do a quick recap on embeddings in general. Basically, embeddings are how large language models store their knowledge of words. They're basically the large language model's dictionary. So in the case of the Gemma model has a total of 262,000 tokens. These are basically all of the words that it knows. Then while in the case of the E2B model, the E2B model stores the meaning of its word as a 1536 vector size. So basically this is how it represents the meaning of a word. So when you bring in a prompt, it basically goes in and it does a quick lookup to get the word. Like take for instance, yeah, it goes in here and gets the vector that represents what's the same with Gemma and the same with is. So the concept of per layer embedding takes input embedding one step further, and it's like, hey, why should we just keep the embedding in the inputs? Why don't we just share it across every layer? Each layer would have their own embedding. Essentially, each layer will have their own dictionary for all the words, and that's exactly what the per layer embedding does. So the per layer embedding has a much more bigger matrix or embedding matrix. This is the same amount of tokens, but the representation is much more larger, and this is actually really big. This makes up to about 2.3 billion parameters alone. So this is quite big. So the idea here is that each layer will have its own embedding, embedding table or embedding matrix or whatever. But currently this is too big. This is just way too big. So rather, let's divide this matrix into subsections. The same amount of tokens are actually represented, but now this time it's been divided into 35, and the representation has reduced. It's no longer 8,000, rather it's 256. So now each layer will have access to a version of this embedding, each layer, and that's why we call it per layer embedding. Okay, so now let's dive in to see how the per layer embedding is actually being used. So one of the cool things I like about the per layer embedding, or one of the reasons why the per layer embeddings were designed, is they're actually not stored in the layer itself, which is funny because they are like per layer embedding, but they're not actually stored in the layer itself. Rather, what the layer does is whenever it needs a word, it basically performs a lookup. So let's say that it's currently working on the word Gemma. Rather than getting in the full, the full embedding, it just gets the word it needs to work on. And this happens across every layer. Every layer works with this. And over the course of the network, in this case, the Gemma E2, if Gemma 4 E2B works with a dimension size of 1536. This doesn't match the 256 vector size or dimension size of the per layer embedding. So what we do is we pass it through a per layer input gate, which transforms this into the same that matches this dimension 256. Then we pass it through a Gelo activation function. This is essentially how the per layer embedding is used. So this Gelo activation function basically tells us, okay, these are the parts of our current existing vector that we really find interesting. Then it gets multiplied with the value that it has gotten from the per layer embedding. And now, once it gets multiplied, this is essentially a gated linear unit. It extracts meaning from both this, it extracts meaning from the extracted embedding and from the activation to create a new vector that sort of like gets the meaning. Like, so it's almost like, okay, the network has already learned a lot while moving. Then it takes this to say, okay, which part of this embedding do I need? Then it creates a new like vector that has this meaning represented. The part it finds really interesting. But once we get here, we need to return it back to the original hidden state size. This is where we pass it through a per layer projection layer, per layer projection gate that will return it back to its original size, and we pass it through an RMS norm, and there's a little bit of residual connection that adds the original vector to it. And this is how per layer embedding works. And it's so interesting because each layer does this. Each layer takes the same word and say that, okay, what meaning? What have I learned about this word? How can I make it? How can I add more stuff to it? And the cool thing about this, across each layer, the model is sort of like not forgetting. It's almost like, imagine if the model at some layer has forgotten the meaning of Gemma, but at some point it gets to in another stage and it just gets the the vector representation of Gemma, and it's like, okay, yeah, this is what Gemma has. So this is basically how they were able to use per layer embedding. Now, what's really interesting about per layer embedding is the fact that this, again, this isn't stored in the model. This is stored in flash memory or SSD, whatever. So this actually makes the model very efficient because it's only working with the per layer inputs. It's never working with the full embedding, but it's still getting the meaning that it desires. Now let's just actually, to see how per layer embeddings were implemented, let's just go through a couple of code snippets for per layer embeddings from the official code release. So if you notice very well, this is like a couple of like code snippets from it, and this is essentially the text decoder of the Gemma 4 model. And we have our forward, our forward pass in the network. And if you notice right here, we have our per layer inputs. This is our per layer inputs. In this case, is Gemma. And notice how the per layer embedding is not in the network itself. So the first thing that happens, first of all, we get our hidden states, which is we store it in the residual that we'll use later. Then we pass it through, we pass our hidden states through this per layer input gates. Then we pass it through the activation function. In this case, is GELU. Then we perform our gated linear unit multiplication, just saying, hey, can I extract the meaning from this, from the embedding that I've gotten? Then again, we pass it back to the per layer projection gate. Then it returns to its original size, and we pass it through normalization, and we do residual connection. So basically, that's the concept of per layer embedding. So now, this is the parameter count of the Gemma E2B model. It has a language model that has about 2.2 billion parameters. It has a vision model that has about 168 million parameters, and the audio model, because it's basically multimodal. Now look at this. This is the per layer embedding. The per layer embedding is 2.3 billion. So this model is actually a 5.1 billion model. But Google is basically saying that no, it's actually not a 5.1 billion parameter model. Why? Because it's saying that this per layer embedding is not stored in the VRAM or in RAM. Rather, it's stored in flash memory. It's stored in SSD. So you're never working with all of this embedding at the same time. So effectively, that's where the E comes from. It's a 2.7 billion parameter model. And what's even more interesting about this is, a lot of times you will not be using the vision model. You will not be using the audio model. So it's even a much more lower model of just basically 2.2 billion parameter. And that's basically where it gets its name from. Gemma E2B, effectively a 2 billion parameter model. Anyway, if you found this video interesting, give it a like and subscribe, because I'll be diving more into the Gemma models. There are lots of interesting things that came out in this release of Gemma.